A significant challenge to validating autonomous vehicles is the fact that they tend to use machine learning-based approaches to perception and other tasks. In a nutshell, machine learning involves an inductive learning approach in which you collect lots of training data, use that training data to learn a model, then you adjust the learned model and iterate until you pass all the tests. In other words, you show the system a lot of examples. This is a person, this is a person, this is not a person, that's a tree, that's a car, and so on. And over many iterations across lots of data, the model is adjusted until it gives statistically very good answers. When you show it a person, almost all the time it'll say, yes, that's a person. When you show it a car, it'll say, yes, that's a car, and so on. There are some fundamental challenges to this approach, though. You're not actually teaching it what a person looks like by describing a person. It's learning by example. Challenges that result from that approach include asking what happens if it sees a novel input. If you've shown it a bunch of people and it sees a person that doesn't quite look like the people it's seen, will it get it right or will it get it wrong? One problem comes with so-called overfitting. If you think about showing machine learning-based system 1,000 pictures of people, if it overfits, it will recognize those exact 1,000 photos and nothing else. So the idea is you want to train it so that it not only recognizes the pictures it's seen, but pictures that are close to the pictures it's seen in some statistical sense. A model that is overfitted is too brittle to small changes in input data and can perform poorly on novel inputs. There's also the possibility of gaps in training data. If there are categories of things that exist in the real world that it's simply never seen, it can't learn them. Those gaps could include skin color, clothing color, unique postures, and so on. Another fundamental challenge is deciding whether it learned what you hoped it learned. Machine learning-based systems are notorious for gaming things. As a purely hypothetical example, if all your training data had people in hats because it was done in a cold winter, then it might struggle with people who don't have hats on because it may not have learned what a person looks like at all. It might simply have learned to recognize hats. While that idea might seem a little far-fetched, in fact, these systems are notorious for gaming easy statistical patterns in data that the people designing the system didn't really realize were there until after they saw the system's behavior. In the end, the fundamental issue for validation is you know the system learned something, and you know that statistically it works pretty well on the inputs you give it for both training and testing. But you don't actually know what it learned. And many times it learns what you hoped it learned, but sometimes it doesn't, and it's very difficult to tell what it may accidentally have learned through accidental patterns in the data that you didn't really even realize were there. There's a famous cartoon that summarizes the quandary of using machine learning-based systems. This cartoon is not entirely fair to the current state of the art, but it illustrates the main issue. You pour the data into this big pile of linear algebra and get an answer out the other side. Well, what if the answers are wrong? Well, stir the pile around until they start looking right. While that may be a bit unfair, it's not a bad explanation of how machine learning-based system training works. And the issue is, you know that the answers to the questions you thought to ask it during testing come out pretty well, but it's difficult to explain why the answers are right and whether or not that's because the system has learned the fundamental concepts you want to teach it, or whether it's just getting lucky.